To look out into the deep, quiet expanses of the night sky is to gaze upon a grand illusion, a shimmering veil of light that hides the true, silent architecture of the cosmos. For what we see, the scattered diamonds of stars, the swirling arms of galaxies, the hot, glowing gas, is merely the foam atop a vast, invisible ocean that stretches through the darkness. We are accustomed to believing that light is the truest messenger of reality, that what glows and shines is what exists. Yet the story of our universe is not written in light, but in the heavy, silent hand of gravity. The primary author of this cosmic history is a ghost, a presence we have never seen, never touched, and never captured, yet without which the very structure of our existence would crumble into dust. This is the story of dark matter, the unseen scaffolding that holds the stars in their orbits, and the slow drift of this mysterious substance as it weaves the great cosmic web, a structure so immense that it defies human comprehension, linking galaxies across billions of light years in a tenuous, invisible lattice. To understand this drift, we must first unlearn the bias of our eyes, which are tuned only to the narrow frequencies of the electromagnetic spectrum, and instead learn to see with the mind, using the language of gravity to map the contours of the dark. Imagine, if you will, that you are floating in the intergalactic void, far from the warmth of any sun, in the deepest, coldest stretches of space between the great clusters of galaxies. Here, the silence is absolute, and the darkness is total, save for the faint, distant smear of island universes, appearing as mere smudges against the velvet black. In this apparent nothingness, you are actually suspended in the thickest part of the universe's skeleton, surrounded by a substance that passes through you as if you were made of mist, a substance that does not interact with light, does not reflect, absorb, or emit any radiation we can detect. Yet it possesses mass, and therefore it possesses gravity. It is here, in the quiet dark, that the universe's true mass resides, flowing in slow, cold rivers that guide the visible matter, the hydrogen, the helium, the dust, into the pools and eddies where stars will eventually ignite. This is the realm of the dark sector, a domain that constitutes roughly 85% of all the matter in the universe, leaving the normal baryonic matter, the stuff of atoms, of us, of the earth, as a mere minority, a dusting of snow on a vast, dark mountain range. The realization that our universe is dominated by this invisible giant did not come as a sudden epiphany, but rather as a slow, creeping unease, a mathematical whisper suggesting that something was wrong with our accounting of the cosmos. It began in the early 20th century, a time when astronomers were just beginning to understand that the Milky Way was not the entirety of the universe, but merely one of countless galaxies drifting through space. In the 1930s, the Swiss astronomer Fritz Zwicky turned his attention to the Coma cluster, a massive aggregation of over 1,000 galaxies located some 320 million light-years from Earth. Zwicky was a man of sharp intellect and often abrasive personality, but his vision was clear. He sought to weigh the cluster, to determine the mass required to bind these hundreds of galaxies together in their gravitational dance. He measured the light coming from the galaxies, estimating their mass based on the number of stars they contained, a standard practice of the time that assumed that mass and light were inextricably linked. But when he measured the speed at which these galaxies were moving, zipping through the cluster at velocities that seemed defyingly fast, he encountered a paradox that would haunt astronomy for decades. The galaxies were moving so rapidly that the visible mass of the cluster, the stars and gas he could see, was nowhere near sufficient to hold them back. By all rights, the Coma cluster should have flown apart billions of years ago, its member galaxies flinging themselves out into the void like stones from a spinning sling. Zwicky realized that for the cluster to remain stable, for gravity to keep a tight grip on these racing galaxies, there had to be more mass, much more mass, hidden within the space between them. He calculated that the cluster required hundreds of times more matter than what was visible to account for the observed velocities. In a stroke of intuition that was decades ahead of its time, he dubbed this missing mass Dunkel Materie, or dark matter. It was a radical suggestion, implying that the universe was filled with invisible material that betrayed its presence only through the force of its gravity. For years, Zwicky's observations remained a curiosity, a jagged edge in the smooth puzzle of cosmology, largely ignored as observational errors or misunderstood physics. The scientific community was not yet ready to accept that the majority of the universe was hiding in plain sight, or rather, hiding in plain darkness. The whisper of dark matter grew into a clamor in the 1970s through the meticulous and transformative work of Vera Rubin and Kent Ford at the Carnegie Institution of Washington. Rubin was interested in the rotation of spiral galaxies, the beautiful, pinwheeling structures like our own Andromeda or the Milky Way. According to the laws of Newtonian physics, and indeed the laws that govern our own solar system, the speed of objects orbiting a massive center should decrease as they get further away from that center. Mercury whips around the sun at a frantic pace, while distant Neptune lumbers slowly along its orbital path. The expectation was that galaxies would behave similarly. The dense concentration of stars in the galactic bulge would dictate the gravitational pull, and the stars in the sparse, outer spiral arms would move slower, trailing off into the quiet of intergalactic space. Rubin pointed her spectrograph at the Andromeda galaxy, measuring the Doppler shift of the stars to determine their rotational velocity. And what she found was a stunning contradiction to the established order. The stars at the very edge of the galaxy were moving just as fast as the stars near the center. The rotation curve did not drop off. It remained flat, extending far out into the dark halo surrounding the visible disk. If the visible stars and gas were the only source of gravity, these outer stars should have flown off into the cosmos, unbound by the galaxy's grip. The fact that they remained tethered, racing at high speeds in stable orbits, implied that the galaxy was embedded in a massive, invisible sphere of matter, a dark halo that extended far beyond the luminous arms. This halo provided the extra gravitational glue needed to hold the high-speed stars in place. Rubin observed this phenomenon in galaxy after galaxy, a systematic anomaly that could not be explained away. The conclusion was inescapable. Galaxies are not merely islands of stars. They are peaks of visible light floating in vast, unseen clouds of dark matter. The visible galaxy is just the tip of the iceberg, the glowing beacon at the center of a much larger, darker structure. This revelation fundamentally shifted our understanding of the cosmos, forcing us to reimagine the universe not as a collection of glowing objects, but as a vast, interconnected web of dark matter, with the visible universe merely tracing the densest knots of this web. We began to understand that dark matter is not just a static filler. It is the architect of the universe. In the earliest moments after the Big Bang, the universe was a hot, dense soup of particles, expanding rapidly. As it expanded, it cooled, and tiny fluctuations in the density of the dark matter began to grow under the influence of gravity. Dark matter, being immune to the pressure of radiation that pushed ordinary matter apart, began to collapse first, pooling into clumps and filaments, creating gravitational wells. These wells acted as seeds. Ordinary matter, hydrogen and helium gas, was drawn into these dark matter wells, falling into the gravitational embrace of the invisible. As the gas accumulated, it compressed and heated up, eventually igniting to form the first stars and galaxies. Thus, every galaxy we see today, every star that twinkles in the night sky, owes its existence to a womb of dark matter that gathered the gas together in the deep past. This structure, this primordial framework, has evolved over 13.8 billion years into what we now call the cosmic web. It is a structure of incomprehensible scale, consisting of vast, thread-like filaments of dark matter that stretch for hundreds of millions of light years, crossing the abyssal voids of the universe. These filaments are the highways of the cosmos. Along them, gas and dark matter flow, drifting slowly toward the massive intersections where the filaments cross. At these intersections, the density is highest. These are the nodes of the web, the locations of the great galaxy clusters like Coma and Virgo. The voids between the filaments are immense regions of emptiness, spanning hundreds of millions of light years, from which matter is slowly draining away, falling toward the filaments and clusters. The universe is therefore not a uniform scattering of galaxies, but a foam-like structure, a cellular network where the walls are made of dark matter and galaxies, and the interiors are empty bubbles of repulsive nothingness. To visualize this, one must imagine the universe as a three-dimensional spiderweb, but one where the silk is invisible and sticky with gravity. We only see the dewdrops caught on the silk, the galaxies, shining in the morning light. We trace the lines of the web by connecting the dots of the galaxies, but the web itself remains hidden. Yet, modern astronomy has given us tools to see this invisible structure through the phenomenon of gravitational lensing. Einstein's general theory of relativity taught us that mass warps the fabric of space-time, creating curves and valleys along which light must travel. When light from a distant galaxy passes through a massive concentration of dark matter, say, a cluster or a thick filament, its path is bent, just as light is bent by a glass lens. This bending distorts the image of the background galaxy, stretching it into arcs or creating multiple images. By carefully analyzing these distortions, astronomers can map the distribution of the mass that caused them. They can reconstruct the topography of the dark matter, creating maps of invisible mountains and valleys, revealing the clumpy, filamentous nature of the dark sector. These maps reveal a universe that is dynamic and slow-moving. Dark matter is not static, it drifts. It is cold in the terminology of cosmology, meaning that its particles move slowly compared to the speed of light, allowing them to clump together under gravity rather than streaming apart. This cold dark matter, CDM, paradigm explains the structure of the universe with remarkable accuracy. Simulations run on the world's most powerful supercomputers, simulations like the Millennium Run or the Illustris project, start with the conditions of the early universe and let the laws of gravity and dark matter physics play out over billions of simulated years. The result is a virtual universe that looks startlingly like the real one. A complex network of filaments, voids, and clusters, a precise match to the large-scale structure we observe in the sky. These simulations show us the slow breathing of the cosmic web, the gradual gravitational collapse that pulls matter from the voids into the filaments, and from the filaments into the clusters, a cosmic flow that has continued for eons. However, the nature of the dark matter particle itself remains one of the deepest mysteries in science. We know what it is not. It is not protons, neutrons, or electrons. It is not black holes, at least not primordial ones in sufficient numbers. It is not neutrinos, which travel too fast to form the clumpy structures we see. The leading candidates are hypothetical particles, like weakly interacting massive particles, WIMPs, or actions, ghostly entities that pass through the Earth and our bodies by the trillions every second, leaving no trace. They interact with our world only through gravity, and perhaps, very rarely, through the weak nuclear force. Deep underground, in mines shielded from cosmic rays, detectors filled with liquid xenon or germanium crystals wait in silence for the faintest nudge of a dark matter particle colliding with an atomic nucleus, a subtle signal that would confirm the existence of this shadow world. But so far, the detectors remain quiet, hearing only the background hum of the universe, leaving us with the macroscopic evidence of the skies, the rotation of galaxies, the lensing of light, the motion of clusters as our only proof. The drift of dark matter is the drift of history itself. It is the slow accumulation of structure in a universe that began as a nearly smooth sea of energy. As we trace the filaments of the cosmic web, we are tracing the lineage of gravity, following the invisible rivers that fed the first galaxies, the tension between the expansion of the universe, driven by the even more mysterious dark energy, and the cohesive pull of dark matter defines the fate of all structure. While dark energy tries to tear the universe apart, stretching the voids and pushing galaxies away from each other, dark matter tries to hold it together, binding the clusters and filaments in a desperate gravitational grip. It is a slow, cosmic tug-of-war played out over billions of years. And for now, the webs of dark matter still hold firm, guiding the slow drift of galaxies through the endless night. As we descend deeper into this narrative, we must prepare to examine the specific mechanics of this web. How does a filament form? What happens when two massive halos of dark matter collide? How does the temperature of dark matter affect the birth of dwarf galaxies? We will journey into the simulation data, visualizing the purple and blue tendrils of the dark web as they span the parsecs. And we will look at the bullet cluster, the smoking gun of dark matter's existence, where the separation of visible gas and invisible mass was caught in a violent celestial crash. We are embarking on a voyage through the unseen, guided only by the warping of light and the whisper of gravity, into the heart of the cold, dark drift. In this epoch, the cosmos was a glowing fog, a dense, hot soup of protons, electrons, and photons, all scattering off one another in a chaotic dance that rendered the universe opaque. A wall of fire stretching in all directions, yet beneath this luminous fog, the dark matter was already at work, silently laying the foundations for everything that was to come. while the ordinary matter, the baryons, was coupled to the radiation, pushed and pulled by the intense pressure of photons, acting like a fluid that sloshed and oscillated in sound waves we call baryon acoustic oscillations. The dark matter remained aloof, indifferent to the radiation, interacting only with gravity. It was the anchor in the storm, the seed of stability. As the universe expanded and cooled, the ordinary matter eventually released its hold on the light, a moment known as recombination, and the universe suddenly became transparent, releasing the oldest light in the cosmos, the cosmic microwave background. If we look closely at this ancient light today, captured by instruments like the Planck Space Telescope, we see a modeled map of faint temperature fluctuations, tiny ripples in the fabric of the early universe. These ripples are not random static. They are the fingerprints of dark matter, the echoes of the gravitational wells that had already begun to form in the deep past, marking the places where the density was slightly higher, where the dark matter had begun to pool, creating the initial blueprint for the cosmic web. From these subtle seeds, the great drift began as the universe stretched outward, fighting the pull of gravity. These overdense regions of dark matter acted as gravitational attractors, slowing the expansion in their local vicinity and eventually reversing it, causing the matter to collapse inward. This process, known as hierarchical clustering, is the primary engine of cosmic construction, a bottom-up method of building a universe where small halos of dark matter form first, collapsing under their own weight, and then slowly merge to form larger and larger structures. It is a process of unhurried violence, a silent accumulation that takes billions of years. Imagine a vast, three-dimensional tapestry of invisible threads, woven from the fabric of space itself. In the early universe, these threads were thin and tenuous. But as the eons passed, the dark matter flowed along them, draining from the voids the great empty bubbles of the cosmos and streaming into the filaments. These filaments are not static lines. They are rivers of mass, dark matter particles, moving under the influence of the collective gravity of the web. Drift along these cosmic highways, winding their way toward the nodes, the dense intersections where the filaments cross. It is here, at the nodes, that the massive galaxy clusters are born, the chaotic, bustling metropolises of the universe, built upon the foundations of the deepest dark matter wells. The behavior of dark matter in these filaments is governed by its cold nature, because the particles move slowly relative to the speed of light. They are easily captured by gravity, allowing them to form fine, detailed structures. If dark matter were hot, composed of fast-moving particles like neutrinos, it would stream out of these wells, washing away the fine details, smoothing out the universe into a featureless sludge. But because it is cold, it clumps. It forms a hierarchy of halos, large halos containing smaller subhalos, nesting like Russian dolls. This is why we see galaxies of all sizes, from the giant ellipticals at the centers of clusters to the tiny, faint dwarf galaxies that orbit them. These dwarf galaxies are the visible tracers of the smaller dark matter subhalos, surviving remnants of the early universe that have not yet been cannibalized by their larger neighbors. The computer simulations that model this process, vast numerical experiments running on supercomputers for months at a time, visualize this evolution in breathtaking detail. In these simulations, the universe begins as a smooth purple mist, which slowly curds and fragments, sharpening into a complex network of bright knots and long, thin tendrils, a structure that looks remarkably like the neural network of a brain or the mycelium of a fungus. This is the skeleton of the cosmos, revealed in silicon, showing us that the visible galaxies are merely the bioluminescent bacteria living on the strands of a much larger, darker organism. As the dark matter flows into these filaments and clusters, it drags the ordinary matter with it. The hydrogen gas, floating in the intergalactic medium, feels the gravitational pull of the dark matter threads and falls in. But unlike dark matter, which can pass through itself without friction, the gas collides. It shocks and heats up as it falls into the gravitational wells, converting its potential energy into heat and light. This is why the filaments of the cosmic web are often traced by hot, ionized gas, glowing in X-rays, a warm, hot intergalactic medium that outlines the dark matter spine. When this gas falls deep enough into the center of a dark matter halo, it cools, condenses, and fragments to form stars. Thus, the galaxy is born, a jewel of light cradled in a vast, rotating sphere of darkness. The dark matter halo extends far beyond the visible edge of the galaxy, 10 times larger and 10 times more massive, a protective cocoon that prevents the galaxy from flying apart. Without this halo, the delicate spiral arms of galaxies, like the Milky Way, would never survive. They are transient patterns, stabilized by the unseen mass, fleeting dreams held together by an invisible thinker. There is perhaps no greater demonstration of this separation between the visible and the invisible, no more dramatic proof of dark matter's independent existence than the catastrophic collision of galaxy clusters. When two of these massive nodes of the cosmic web are drawn together by their mutual gravity, they do not merge gently. They crash with the energy of a billion supernovae. The most famous of these events is the Bullet Cluster, 1E0657-56. Here, we witness the aftermath of a high-speed impact between two enormous clusters of galaxies. The collision was a sorting machine, a cosmic sieve that separated the components of the universe based on their nature, the stars within the galaxies being incredibly sparse relative to the space between them, passed right through each other like two swarms of bees, largely unaffected by the collision. The hot gas, however, which makes up the majority of the normal matter in a cluster, slammed together. It created a shock wave, a drag force that slowed the gas down, causing it to lag behind, stuck in the center of the collision zone, glowing furiously in X-rays due to the intense heating. But the dark matter, the ghost, behaved differently because dark matter does not interact with light and interacts only weakly, if at all, with itself. It experienced no friction. It did not splash. It did not shock. It simply passed through the other dark matter halo, ghost through ghost, continuing on its trajectory with the stars. When astronomers looked at the bullet cluster, they saw the visible evidence of this separation. They used gravitational lensing to map the mass, to find where the gravity was coming from. If there were no dark matter, the gravity should be centered where the gas is, for the gas contains far more mass than the stars. But the lensing maps revealed that the gravity was not with the gas. It was with the stars, in two massive clumps on either side of the gas cloud. The mass had moved on, leaving the normal matter behind. The dark matter had drifted through the violence of the crash, indifferent to the friction that halted the gas. This observation provided the most direct empirical proof of dark matter's existence, shattering alternative theories that tried to explain the universe by merely tweaking the laws of gravity. Here was matter that we could not see, separating itself from the matter we could see, proving that the universe is composed of two distinct fluids, one that glows and churns and interacts, and one that drifts in silence, dominating the gravitational landscape. This drift is not merely a thing of the past. It is happening now, in the slow, inexorable flow of the local universe. Our own Milky Way is falling. We are falling towards the Andromeda galaxy, destined to collide and merge in 4 billion years. A dance choreographed by the dark matter halos that envelop us both. But on a larger scale, our entire local group of galaxies is drifting at over 600 kilometers per second towards a region of space known as the Great Attractor, a massive concentration of mass hidden behind the dust of our own galactic plane. And beyond that, the Great Attractor itself is being pulled towards an even larger structure, the Shapley supercluster, a monster node in the cosmic web containing tens of thousands of galaxies. We are caught in a great river of dark matter, a flow known as the dark flow, sliding along the filaments towards the densest regions of the universe. This motion is smooth, continuous, and unrelenting. It is the breathing of the cosmos, the rearrangement of matter on scales so vast that a human lifetime is less than a flickering nanosecond in comparison. Yet within this grand drift, there are subtleties, fine-grained details that challenge our understanding. As we zoom in from the scale of superclusters to the scale of individual galaxies, the interplay between dark matter and ordinary matter becomes more complex. In the centers of galaxies, the density of ordinary matter, stars, and gas can become so high that it begins to dominate the local gravity, altering the distribution of the dark matter itself. This baryonic feedback is a subject of intense study when massive stars explode as supernova, or when supermassive black holes at galactic centers erupt with jets of energy. They can blow gas out of the galaxy entirely. This sudden removal of mass changes the gravitational potential, causing the dark matter halo to expand, to puff up. It is a dynamic feedback loop. The dark matter concentrates the gas to form stars, and the death of those stars pushes back against the dark matter, reshaping the very cradle that born them. This breathing of the halo, this response of the dark sector to the violent astrophysics of the visible sector, suggests a relationship that is more symbiotic than previously thought. The ghost guides the machine, but the machine can, in turn, shift the ghost. The texture of the cosmic web is also defined by what is absent, the voids, those vast, spherical regions of emptiness that occupy most of the volume of the universe, are not truly empty. They are underdense regions, containing perhaps only 10% of the average density of the universe, but they are the laboratories of the isolated. In these lonely expanses, far from the bustling filaments and clusters, small ripples of dark matter can still collapse to form isolated dwarf galaxies, hermits of the cosmos. These void galaxies are pristine, untouched by the interactions and mergers that shape galaxies in the crowded clusters. They drift in solitude, evolving slowly, their dark matter halos distinct and undisturbed. Studying these lonely outposts allows astronomers to test their models of dark matter in a clean environment, away from the chaotic astrophysics of the dense web. And even in the deepest voids, the faint structure of the web persists. Tenuous, wispy filaments of dark matter crisscross the emptiness, too thin to trap much gas, too weak to form many stars, but they're nonetheless a subtle geometry in the nothingness. As we ponder this invisible lattice, we must also consider the role of time. The web we see today is not the web that will exist tomorrow. The universe is caught in a battle between two titans. The attractive pull of dark matter, which seeks to build structure, to pull everything into a single, massive knot, and the repulsive push of dark energy, which seeks to tear the web apart, to stretch the voids until the filaments snap, and the clusters are isolated islands in an expanding sea of dark. For the first half of the universe's life, dark matter was winning. The web grew, the clusters formed, the structure sharpened. But about 5 billion years ago, the balance shifted. Dark energy began to dominate. The expansion of the universe accelerated. Today, we are living in a time when the growth of the cosmic web is slowing down. The Great Drift is fighting against the stretching of space itself. Distant clusters are being carried away from us faster than light can bridge the gap. The filaments are being stretched thin. In the far, far future, the cosmic web may dissolve, the glorious tapestry unraveling as the universe expands into a cold, dark isolation. But for now, the web holds. The dark matter continues its slow work, binding the galaxy clusters, holding the spiral arms of the Milky Way, and guiding the light of distant quasars through the gravitational lenses of the deep. We construct our understanding of this dark architecture through a combination of observation and simulation, effectively reverse engineering the universe by measuring the distortion of light from millions of distant galaxies, a technique called weak gravitational lensing. Astronomers are creating three-dimensional maps of the dark matter distribution. Projects like the Dark Energy Survey and the Euclid mission are scanning vast swaths of the sky, measuring the shapes of galaxies with exquisite precision. They look for the tiniest alignments, the subtle tendency of galaxies to align with the invisible shear of the foreground dark matter. These statistical signals, averaged over millions of objects, reveal the clumping and the drifting of the dark sector. The maps they produce are not of light, but of density. They show us the mountains of mass rising from the plains of the voids. They confirm that the visible galaxies truly are tracing the dark matter skeleton. But they also reveal the subtle offsets, the complexities where the gas and the dark matter do not perfectly align. Hints of the complex hydrodynamic physics at play in the Grand Drift. To visualize the scale of a dark matter filament, imagine a bridge of matter connecting two galaxy clusters separated by 50 million light years. This bridge is not a solid object, but a stream. If you were to float inside it, you would see galaxies drifting past you, carried along the current of the dark matter river. You would see gas clouds, tenuous and hot, stretching along the axis of the filament, and all around you, the invisible particles of dark matter would be swarming, passing through you, through the galaxies, through everything, bound only by the grand gravitational potential of the filament itself. It is a structure of tenuous majesty, a river of ghosts spanning the abyss, and it is the dominant feature of our universe. The stars, the planets, the life forms, we are all just flotsam caught in the eddies of this great, dark flow. While the great filaments of the cosmic web stretch across the voids, weaving the skeleton of the universe on scales that defy human imagination, there is a more intimate, ghostly drift happening right here, within the immediate vicinity of our own planet. We must now shift our gaze from the telescopic to the microscopic, from the light years of intergalactic space to the femtometers of the subatomic realm. For the story of dark matter is not just written in the architecture of galaxy clusters, but in the silent, incessant flow of particles that passes through the Earth every single moment as our solar system orbits the center of the Milky Way, traveling at a speed of 220 kilometers per second. We are not moving through empty space. We are plowing through the dark matter halo that envelops our galaxy. This creates a dark matter wind, a constant breeze of invisible particles that washes over us, passing through the atmosphere, through the bedrock of our continents, through the concrete of our cities, and through our own bodies, leaving no trace, no ripple, no sensation. To these particles, the solid matter of our world is as tenuous as a mist. The electromagnetic forces that bind our atoms together, giving walls their solidity and the ground its firmness, are invisible to them. They feel only gravity, and perhaps the weak nuclear force, meaning they glide through the electrical fields of our atoms like a phantom walking through a wall. This local drift is the subject of one of the most intense and quietest scientific endeavors in human history, the direct search for dark matter. Because we cannot see it in the sky with conventional telescopes, we have decided to build traps, waiting for the 1 in a trillion moment when a dark matter particle might accidentally collide with an atom of ordinary matter. To hear this faint whisper, we must escape the noise of the surface world. We must go deep underground, burying our ears beneath kilometers of rock to shield our delicate instruments from the cosmic rays that constantly rain down from the sky. In the deep mines of South Dakota, in the tunnels beneath the Gran Sasso Mountains in Italy, and in the nickel mines of Sudbury, Canada, physicists have constructed cathedrals of silence. Here, in the cool, dark caverns, reside the detectors, great tanks filled with noble liquids like xenon or argon, chilled to temperatures that would freeze the air instantly. Consider the xenon experiment or the LUX Zeppelin detector. These are vessels filled with tons of liquid xenon, a dense, transparent fluid. The principle is one of agonizing patience. The scientists wait for a particle from the dark matter wind, a weakly interacting massive particle, or WIMP to strike a xenon nucleus. If such a collision occurs, the nucleus will recoil, releasing a tiny flash of light, a scintillation, and liberating a handful of electrons. Photomultiplier tubes lining the tank, sensitive enough to detect a single photon, watch the darkness of the liquid, waiting for that specific telltale signature. The rock above blocks the noisy cosmic rays. The purity of the materials blocks the radiation from the detector itself. It is a vigil kept in the dark, a hunt for a ghost in a sealed room. For decades, these detectors have run, staring into the liquid, pushing the limits of sensitivity further and further down. They have heard the background chatter of neutrinos, the subtle decay of impurities, but the dark matter particle remains elusive. The silence of these detectors is profound. It tells us that dark matter interacts even less frequently than we had hoped, that it is even more ghostly, even more detached from our luminous world than the simplest theories predicted. This silence has forced us to reconsider the nature of the drift. For a long time, the leading theory was supersymmetry, a beautiful extension of the standard model of particle physics, which posits that every known particle has a heavier, invisible partner. The WIMP was the natural candidate emerging from this mathematics, a particle with the mass of a heavy atomic nucleus that was produced in the thermal bath of the Big Bang. But as the Large Hadron Collider smashes protons together at energies that recreate the conditions of the early universe, and as the underground detectors remain quiet, the WIMP hypothesis is under siege. We are beginning to wonder if we are looking for the wrong kind of ghost. Perhaps dark matter is not a heavy particle, but something incredibly light, something that behaves more like a wave than a point-like object. Enter the action, a hypothetical particle originally proposed to solve a completely different problem in quantum chromodynamics related to the symmetry of the neutron. Actions would be billions of times lighter than an electron, so light that their quantum wavelengths would overlap, causing them to behave like a vast, coherent field, a Bose-Einstein condensate on a galactic scale. If the dark matter halo is made of actions, the drift is not a rain of bullets, but the oscillation of a wave. To catch an action, you do not use a tank of liquid xenon. You use a resonant cavity, a metal box placed in a strong magnetic field. The theory suggests that in the presence of a magnetic field, an action can occasionally convert into a photon, a particle of light. Experiments like the Action Dark Matter E experiment, or ADMX, are essentially radio receivers, tuning a dial through the frequencies of the cosmos, listening for the faint hum that would signal the conversion of dark matter into radio waves. It is a search for a cosmic radio station that has been broadcasting since the dawn of time, a station we are only just learning how to tune into. While the particle physicists hunt in the deep earth, the astrophysicists look back to the sky, finding that the cold dark matter model, despite its success in explaining the large-scale web, faces challenges when we zoom in to the scale of individual galaxies. This is where the drift becomes turbulent. In the simulations where dark matter is perfectly cold and interacts only via gravity, the centers of galaxies should be incredibly dense with dark matter, forming a sharp peak or cusp. However, when we observe real dwarf galaxies, measuring the rotation of their stars to infer the density profile, we often see a core, a central region where the dark matter density is flat, constant, rather than peaking sharply. This discrepancy is known as the core cusp problem. It is a subtle mismatch, a hint that perhaps dark matter is not perfectly cold, or that the physics of the ordinary matter, the exploding stars, the winds from black holes, is churning the dark matter, heating it up and pushing it out from the center. Furthermore, the simulations predict thousands of tiny satellite galaxies swarming around a giant like the Milky Way, a buzzing hive of subhalos. Yet for a long time, we saw only a dozen or so bright satellites, the Magellanic Clouds, Draco, Ursa Minor. This missing satellites problem troubled astronomers for years. Where were the thousands of other subhalos? Were they there, but dark, devoid of stars? Or did they never form? In recent years, deep surveys like the Dark Energy Survey have begun to find faint, ultra-diffuse ghost galaxies, wisps of stars barely brighter than the background sky, suggesting that many of the missing satellites are there, just incredibly hard to see. But the numbers still don't quite match the pure, cold, dark matter predictions. This has led to the proposal of warm dark matter, particles that move faster than WIMPs, blurring out the smallest clumps, preventing the tiniest subhalos from forming. Or perhaps self-interacting dark matter, where the dark particles can bounce off one another, creating a pressure that smooths out the dense cusps at the centers of galaxies. This interplay between the smooth, large-scale drift and the messy, small-scale physics creates a picture of a universe that is both simpler and more complex than we imagined. The dark matter is not just a rigid scaffolding. It is a fluid that responds to its environment. It drifts, it clumps, it may even collide with itself. The drift is a dynamic process. Imagine the dark matter halo of the Milky Way not as a static sphere, but as a living ocean with tides and currents. When a smaller galaxy falls into the Milky Way, its dark matter halo is stripped away by tidal forces, creating long streams of dark matter that wrap around our galaxy like ribbons. We are currently detecting streams of stars, like the Sagittarius stream, that are the debris of these cannibalized galaxies. These stellar streams are riding on invisible rivers of dark matter. By mapping the motion of the stars in these streams, we can trace the shape of the dark matter river underneath. If the dark matter halo is lumpy, the streams should be disturbed, showing gaps and kinks where a subhalo of pure dark matter passed through. We are looking for these gaps now, hunting for the dark impactors, invisible clumps that possess no stars but have enough gravity to punch a hole in a stream of stars. There is a profound beauty in this slow, invisible violence. The universe is a place of constant consumption and growth. Dark matter drives the mergers. It brings galaxies together, its friction slowing them down so they can coalesce. Without the drift of dark matter, galaxies would fly past one another in the expanding universe, lonely ships in the night. Dark matter is the friction, the glue, the gravity that allows complexity to emerge. It allowed the gas to pool, the stars to ignite, and the heavy elements to be forged. In a very real sense, we are the children of the dark drift. Our carbon, our oxygen, our iron, all forged in stars that formed only because dark matter created the gravitational wells to hold the gas. We are the visible foam on the dark ocean as we stare into the liquid xenon, waiting for a spark, or peer into the voids of space, mapping the distortions of light. We are engaging in a conversation with the invisible. We are asking the universe to reveal its hidden face. The fact that 85% of the matter in the cosmos is unknown to us is not a failure of science. It is the fuel of our curiosity. It tells us that there are forces and particles waiting to be discovered that could rewrite the laws of physics. The drift of dark matter through the cosmic web is the drift of a mystery that spans the entire history of time. From the first moments of the Big Bang to the final fading of the last star, it connects the largest scales of the filaments to the smallest scales of the particle detectors. It is a single, continuous story of gravity's silent, patient work. Let us return to the image of the web. The nodes, the clusters, are the cities of the universe, blazing with X-ray light, filled with thousands of galaxies. The filaments are the highways, the dark roads along which matter flows. And the voids are the wilderness, the empty deserts. But even the voids are not truly empty. They are expanding, pushing the filaments apart. This brings us to the final, and perhaps most unsettling, player in our story: dark energy. While dark matter pulls, dark energy pushes. While dark matter builds the web, dark energy stretches it. We are living in the era of the cosmic tug of war. For billions of years, dark matter held the upper hand, and the universe slowed down its expansion, allowing the web to form. But about 5 or 6 billion years ago, the density of matter dropped enough due to expansion that dark energy took over. The expansion began to accelerate. The drift is now fighting a current that seeks to disperse it. This acceleration means that the cosmic web is freezing in place. The flow of matter from the voids into the filaments is slowing down as the voids expand faster than the matter can fall. The largest structures in the universe, the superclusters, are likely the last ones that will ever form. Gravity can no longer bridge the ever-widening gaps. We are witnessing the peak of cosmic structure. In the far future, the filaments will snap. The clusters will become isolated islands, and the sky will go dark as the other galaxies are carried away beyond the cosmic horizon. The drift of dark matter will eventually cease to build. It will only hold what it has already gathered. We are privileged to live in this golden age of structure, where the web is vibrant, connected, and visible, where we can trace the flow of the ghost and marvel at the architecture of the night. The search continues. New telescopes are being built, the Vera Rubin Observatory, which will map billions of galaxies, creating a movie of the universe that will reveal the shimmy and shake of the dark matter web over time. The Euclid mission, launching to space to measure the shapes of galaxies with unprecedented clarity. These instruments will turn the sky into a laboratory. They will test if dark matter is truly cold or if it has some warmth. They will test if it interacts with itself. They will map the detailed tomography of the dark universe. We are drawing a map of a land we cannot see, feeling the contours of the mountains with the tips of our fingers, guided by the light of the stars. The drift is slow, but our understanding is accelerating. We are learning to read the invisible, to hear the silence, and to appreciate the vast, dark scaffolding that holds us all. To witness the physical reality of these invisible highways, we must turn our attention to the specific, tangible discoveries that have transformed the cosmic web from a theoretical construct into an observational certainty. For decades, the filaments were ghosts in the machine, lines drawn by computer algorithms connecting the bright dots of galaxy clusters. But in 2012, a team of astronomers achieved something remarkable. They captured the shadow of a filament itself between the two massive galaxy clusters, Able 222 and Able 223, separated by some 40 million light-years, lies a bridge to the optical telescopes that scan the sky. The space between these clusters appeared largely empty, a void sprinkled with a few wayward galaxies. But when the astronomers applied the technique of weak gravitational lensing, analyzing the subtle distortions of the background light, the ghost revealed its shape. They found a massive ridge of dark matter connecting the two clusters, a dense, thick cord of invisible mass containing more material than the clusters themselves. This was the first robust detection of a dark matter filament, a physical confirmation that the clusters are not isolated islands, but are nodes in a continuous, flowing geography. The dark matter in this bridge is not stagnant. It is a conduit. We must imagine the gravitational potential of this filament as a deep valley in the fabric of space-time, a trough along which matter, both dark and visible, slides. The galaxies caught in this trough are like beads sliding down a string, accelerating toward the clusters at either end, driven by the relentless pull of the nodes. This journey along the filaments is not without consequence for the galaxies themselves. The drift is a transformative process, a passage that alters the destiny of the travelers as galaxies move from the lonely, low-density voids into the denser environment of the filaments, and eventually into the chaotic hearts of the clusters. They undergo a metamorphosis, often described with a somber biological analogy. They die. Astronomers categorize galaxies into two broad color camps. The blue cloud, consisting of active, spiral galaxies rich in gas and newborn stars, and the red sequence, populated by elliptical, gas-poor galaxies where star formation has ceased. The transition from blue to red is the transition from life to stellar death, and the cosmic web is the killing floor as a blue spiral galaxy drifts along a dark matter filament and approaches a massive cluster. It encounters the hot, tenuous gas that permeates the structure, the intracluster medium. The galaxy, moving at thousands of kilometers per second, plows through this stationary gas. The resulting wind is fierce, acting like a cosmic leaf blower that strips the galaxy of its own internal gas, the fuel for future stars. This process, known as ram pressure stripping, effectively strangles the galaxy. The dark matter plays the role of the trap. Its gravity accelerates the galaxy to the high speeds necessary for this stripping to occur, and its deep potential well holds the hot gas in place, creating the resistive medium. We see the aftermath of this violence in jellyfish galaxies, objects that exhibit long tentacles of stripped gas trailing behind them, glowing with the light of young stars formed in the wake of the destruction. These tentacles trace the path of the galaxy through the dark matter halo, marking its trajectory as it falls. Eventually, the galaxy is drained. It loses its spiral arms. Its blue hue fades to a dull red as the massive, short-lived stars die out, leaving only the long-lived, cool dwarfs. It settles into the center of the cluster, joining the swarm of other red and dead ellipticals. A graveyard of galaxies bound forever by the gravity of the dark node. Thus, the drift through the cosmic web is a journey of maturation and eventual obsolescence, a cosmic aging process dictated by the density of the dark environment. To fully appreciate the scope of this drift, we must look even further back, past the formation of the current web, to the epoch known as the cosmic dawn. Before there were stars to strip, before there were galaxies to quench, there was only the dark. About 100 million years after the Big Bang, the universe was dark, filled with neutral hydrogen gas and the slowly collapsing halos of dark matter. These first halos, much smaller than the Milky Way, mere mini-halos, were the incubators of the first light. In the silence of the dark ages, the neutral hydrogen fell into these mini-halos, cooling and condensing until the pressure ignited the very first generation of stars, the population Roman 3 stars. These were monsters, hundreds of times more massive than our sun, burning with a ferocious ultraviolet intensity. They were the first lighthouses in the dark ocean. The structure of the dark matter determined where these lights would turn on. The first stars did not appear randomly. They appeared in the highest peaks of the dark matter density field. The drift of baryons into these primordial dark wells ended the cosmic dark ages, initiating the epoch of reionization, where the ultraviolet light from the first stars and quasars began to burn away the neutral fog of hydrogen, rendering the universe transparent. We are on the verge of mapping this ancient era with radio telescopes like the Square Kilometer Array, SKA. These instruments will look for the 21 centimeter line, a specific radio wavelength emitted by neutral hydrogen. By mapping the intensity of this signal across the sky, we will be able to see the Swiss cheese structure of reionization, bubbles of ionized, transparent space growing around the first dark matter halos, expanding and merging until the fog was cleared. This map will effectively be a map of the dark matter skeleton as it existed 13 billion years ago, the earliest blueprint of the web. Yet, even as we build this consistent, triumphant narrative of cold dark matter, we must acknowledge the persistent whisper of dissent, the scientific tension that keeps the field honest. There exists a small but vocal contingency of physicists who argue that the dark sector is an illusion, a phantom created by our misunderstanding of gravity itself. This hypothesis, known as modified Newtonian dynamics, MIND, suggests that there is no invisible matter, but rather that the laws of gravity change at extremely low accelerations, such as those found in the outer rims of galaxies. MIND can eerily reproduce the rotation curves of spiral galaxies without a single ounce of dark matter, simply by tweaking the equations of Newton and Einstein. It is an elegant mathematical solution that removes the need for a ghost. However, MIND struggles to explain the universe on the largest scales. It falters when faced with the cosmic microwave background, and it cannot easily account for the bullet cluster, where the gravitational lensing clearly separates from the visible matter. The drift of the dark matter, as evidenced by the large-scale web and the separation of mass in collisions, remains the most robust explanation we have. The majority of evidence points not to a modification of the laws, but to the existence of the stuff, the substance, the cold fluid that fills the dark. This substance, while invisible, acts as a lens for the entire universe. The cosmic microwave background. CMB, the afterglow of the Big Bang, must travel for 13.8 billion years to reach our detectors. As it travels, it passes through the evolving cosmic web, through the filaments and the growing clusters. The gravity of these dark matter structures bends the path of the CMB photons, slightly distorting the pattern of hot and cold spots. This phenomenon, known as CMB lensing, allows us to create a map of all the mass in the visible universe, integrated along the line of sight. The Planck satellite has produced such a map, a modeled sphere that looks like a dirty window. This dirt is the dark matter. By cleaning the window, by analyzing the statistical properties of the distortions, we have confirmed that the web is there, extending all the way back to the surface of last scattering. We see the potential wells of the dark matter deep in the past, and we see how they have grown. The agreement between the predicted growth of dark matter structure and the observed lensing map is one of the triumphs of modern cosmology, a confirmation that our model of the slow, cold drift is correct to an astonishing degree of precision. Let us descend again from the cosmic scale to the intimate physics of the halo. We must consider the substructure crisis in more detail. If dark matter is truly cold and collisionless, the Milky Way should be swarming with thousands of tiny, dark clumps, the failed seeds of galaxies. We call these dark matter clumps, or subhalos. While we have found some faint satellite galaxies, many subhalos should be completely dark, having never managed to attract enough gas to form stars. These invisible prowlers drift through our galactic neighborhood, unseen, but perhaps not unfelt. It has been proposed that the gravitational influence of a passing dark subhalo could disturb the delicate disk of our galaxy, causing ripples and warps. Some astronomers analyze the vertical motion of stars in the Milky Way's disk, looking for the breathing mode or bending mode oscillations that would signal a recent flyby of a dark object. We are checking the seismology of the galaxy for the footsteps of ghosts. Furthermore, these dark clumps might act as lenses on a microscale. If a dark subhalo passes in front of a distant star, its gravity will momentarily brighten the star, a phenomenon called microlensing. Surveys watching millions of stars in the Magellanic Clouds or the galactic bulge are hunting for these brief flickers. It is a search for the invisible needle in the haystack of light. If we find them, if we can prove that the halo is grainy and full of lumps rather than smooth, we will have validated the cold, dark matter model. If the halo proves to be smooth, we may have to embrace warmer or more exotic forms of dark matter, implying that the ghost is more ethereal than we thought. There is also the question of dark matter annihilation. In some theories, particularly those involving WIMPs, dark matter is its own antiparticle. When two dark matter particles collide in the dense center of a galaxy or a cluster, they should annihilate each other, releasing a burst of energy in the form of gamma rays. Telescopes, like the Fermi Gamma Ray Space Telescope, have been staring at the centers of the Milky Way and nearby dwarf galaxies, looking for this excess radiation, a glow that cannot be explained by pulsars or black holes. There have been hints, an unexpected galactic center excess of gamma rays that initially caused a wave of excitement. Was this the signal of the dark matter drift consuming itself? The debate rages on. Some argue it is indeed the signature of dark matter. Others contend it is merely a population of unresolved millisecond pulsars, spinning neutron stars that mimic the signal. The thermal signature of the drift is still ambiguous, a warm spot in the data that refuses to resolve into a clear picture. The complexity of the cosmic web is also a story of hydrodynamics, the physics of fluids. The ordinary matter, the gas, does not just passively follow the dark matter, it pushes back. We must imagine the cosmic web not just as a gravitational skeleton, but as a system of feedback. When a supermassive black hole at the center of a galaxy cluster erupts, it launches jets of plasma near the speed of light. These jets inflate massive bubbles in the hot intracluster medium, shock waves that ripple out for hundreds of thousands of light years. These outbursts inject energy into the surrounding environment, preventing the gas from cooling and falling further into the dark matter well. This stops star formation. It keeps the galaxy red and dead. The black hole, a speck compared to the size of the cluster, regulates the growth of the entire system. It is a feedback loop connecting the smallest scales, the event horizon, to the largest scales, the dark matter halo. The drift of the gas is arrested by the fury of the central engine. Simulations that include this AGN feedback, active galactic nucleus feedback, produce galaxies that look much more like the real universe than simulations that only include gravity. The dark matter builds the stage, but the black holes dictate the lighting and the mood of the play. As we ponder the future of this research, we must look to the next generation of maps. The Euclid mission, launched by the European Space Agency, and the upcoming Nancy Grace Roman Space Telescope by NASA, are designed to conduct tomography of the universe. They will slice the cosmos into time shells, measuring the distribution of dark matter at different epochs. This will allow us to make a movie of the drift. We will see empirically how the web tightened over time. We will measure the growth rate of structure, a parameter that tells us how fast gravity is pulling things together versus how fast dark energy is pushing them apart. If the growth rate deviates from our predictions, it could signal a breakdown of general relativity on cosmic scales. A hint that gravity itself is more complex than Einstein dreamed. The study of dark matter is, in essence, the study of humility. We are the minority, the atoms in our bodies, the rock of the earth, the plasma of the sun. This is the exotic matter. The normal state of the universe is dark, cold, and invisible. We are the rare, glowing anomalies, the bioluminescence on the surface of the deep sea. The drift of the dark matter is the primary motion of reality. Our movements, our orbits, our galactic rotations are merely the secondary responses to that great, unseen current. To understand the web is to understand our place. We are residents of a small, glowing node, drifting along a filament of shadow, caught in a gravitational tide that began before the first star ignited and will continue long after the last star fades. In the final segment of this narrative, we will turn our eyes to the ultimate fate of the web. We will explore the theoretical end states of the universe, the big freeze, the big rip, or the vacuum decay, and how dark matter dictates these scenarios. We will summarize the grand journey we have taken, from the initial density fluctuations to the vast superclusters. And we will close with a meditation on the philosophical implications of living in a universe where the most important substance is one we cannot see. The drift continues, carrying us toward an uncertain but magnificent future. We must now cast our minds forward, beyond the eras of human history, beyond the lifetime of the sun, and into the deep, unfathomable expanses of the cosmic future. For the story of dark matter is not merely a history of the past, but a prophecy of the end. The cosmic web, that grand, invisible cathedral we have spent so long mapping, is not a permanent fixture of reality. It is an ephemeral structure, a momentary gathering of ghosts in the vastness of time. We are currently living in the peak era of the web, the stellariferous era, where the filaments are thick with galaxies, and the nodes are bright with the fire of fusion. But the seeds of the web's destruction were sown in the very energy of the vacuum itself. We have spoken of the drift, the gravitational pull that draws matter together. But we must now confront the drift's great adversary, the accelerating expansion of the universe, driven by the enigmatic force known as dark energy. This force, which constitutes nearly 70% of the energy budget of the cosmos, acts as a relentless anti-gravity, a pressure that swells the space between the galaxies. For the first few billion years of the universe, the density of dark matter was high enough to act as a brake, slowing the expansion and allowing the web to weave itself into existence. But as the universe grew, the dark matter was diluted, spread thinner and thinner across the widening void. Dark energy, however, is a property of space itself, it does not dilute. As more space is created, more dark energy appears, its strength remaining constant per unit of volume. Approximately 5 billion years ago, the scales tipped. The jerk of the universe occurred, a transition where the braking ceased and the accelerator was pressed. We are now coasting into a future where the expansion is exponential, a runaway train that threatens to tear the cosmic web asunder. The first casualties of this war will be the filaments, these tenuous bridges of dark matter and gas, which currently funnel nutrients into the galaxy clusters, are being stretched. As the voids expand, the filaments are becoming longer and thinner. Eventually, the expansion will be too fast for the dark matter particles to overcome. The gravitational flow will be arrested. The river will run dry. The supply of fresh gas falling into the clusters will cease, and the filaments will snap, dissolving into the background density of the universe. The great highway system of the cosmos will be dismantled, leaving the galaxy clusters as isolated archipelagos in an ever-widening ocean of dark. This process is already beginning. The largest superclusters we see today are likely the largest structures that will ever form. The drift has hit a wall. The era of construction is ending, and the era of isolation is beginning. Let us focus on the fate of our own home, the local group. We are bound by gravity to the Andromeda galaxy and a retinue of smaller dwarf galaxies. This local knot of dark matter is dense enough to resist the push of dark energy. The expansion of the universe will not tear the Milky Way apart, nor will it separate us from Andromeda. In fact, the drift here is destined for a violent but creative climax in approximately 4 to 5 billion years, just as our sun swells into a red giant and consumes the inner planets. The Milky Way and Andromeda will collide. It will not be a collision of stars, but a merger of halos. The two great spheres of dark matter will pass through each other, oscillate, and eventually settle into a single, massive, football-shaped halo. The spiral arms will be destroyed. The gas will be consumed in a final, brilliant burst of star formation, and the two galaxies will become one giant elliptical galaxy, often dubbed Milkomda. However, while we merge with our neighbor, the rest of the universe will be waving goodbye as the expansion accelerates. The distant galaxy clusters, the Virgo cluster, the Coma cluster, the Great Walls and filaments, will be carried away from us at speeds exceeding the speed of light. They will cross the cosmic event horizon, a point of no return beyond which no light can ever reach us. One by one, the galaxies will blink out of the sky, redshifted into invisibility, their photons stretched to infinite wavelengths. In 1 trillion years, an observer standing on a planet around a red dwarf star in Milkomda will look up and see nothing, no other galaxies, no cosmic web, no background radiation, for the cosmic microwave background will have faded to an undetectable whisper. To these future astronomers, the universe will appear static, eternal, and limited to their own single island of stars. They will have no way of knowing that there was once a vast web, no way of knowing about the Big Bang, no way of knowing that the dark matter halo they inhabit is just one of billions that have drifted away into the void. The evidence of cosmology itself will be erased by the expansion. We are privileged to live in the brief window of time where we can see the web, where we can trace the drift, where the history of the universe is written in the sky for us to read. In this deep future, the nature of the dark matter drift will change. With no external galaxies to interact with, no fresh gas falling in from the filaments, the Milcombe galaxy will settle into a long, quiet senescence. The dark matter halo will become a relaxation machine. Over countless eons, the gravitational interactions between the dark matter particles and the stars will exchange energy. This process, known as dynamical friction, will cause the lighter objects, the stars, to gain energy and migrate to the outskirts of the halo, while the heavier objects, black holes, and neutron stars will lose energy and sink to the center. The galaxy will stratify. The dark matter itself, if it is made of WIMPs, may continue to annihilate in the dense center, providing a faint, steady source of gamma rays, a dying ember in the heart of the galaxy. But there are other, more exotic possibilities for the end of the drift, depending on the precise nature of dark energy. If dark energy is truly a cosmological constant, represented by lambda in Einstein's equations, then the expansion will continue at a steady, exponential rate, leading to the big freeze, or heat death described above. The universe effectively becomes empty and cold, a vacuum dominated by the lonely drift of isolated particles. However, if dark energy is phantom energy, a substance where the density increases with time, then we face the big rip. In this terrifying scenario, the phantom energy becomes so strong that it overcomes all gravitational bonds. First, it would tear the galaxy clusters apart, dissolving the web. Then it would rip the galaxies themselves to pieces, unbinding the stars from the dark matter halos. Then it would tear solar systems apart, ripping planets from their stars. Finally, in the last fraction of a second, it would overcome the electromagnetic and nuclear forces, ripping atoms apart, leaving the universe as a sea of subatomic particles, unable to interact. The drift would end in a shredding of reality itself. While current data suggests this is unlikely, preferring the big freeze, the dark sector holds enough mysteries that we cannot rule it out entirely. There is also the question of the stability of dark matter itself. Is it truly stable? Protons, the building blocks of our visible world, are thought to be stable for at least 10 to the power of 34 years, But what of the dark particle? If dark matter decays, even on a timescale of trillions of years, the web will eventually evaporate. Imagine the invisible skeleton of the universe slowly turning into radiation, into neutrinos or photons. As the dark matter decays, the gravitational potential wells would shallow. The galaxies, no longer held together by the heavy hand of the halo, would expand and dissolve. The stars would drift away from one another, unbound, wandering alone into the dark. The web would not just be stretched by dark energy. It would sublimate, turning from solid ice to gas, leaving behind a universe of pure radiation, a sea of light with no eyes to see it. Yet, even in the face of these immense timescales and terminal destinies, the current drift remains a thing of profound beauty and complexity. We are learning that the dark matter is not just a background stage. It is a reservoir of history, the phase space of dark matter, the record of the positions and velocities of every particle, encodes the memory of everything that has happened, every merger, every collision, every collapse is written in the twists and folds of the dark matter sheet. Theoreticians speak of the dark matter sheet folding in on itself in six-dimensional phase space, like a piece of origami folded billions of times. The galaxies are merely the places where the paper is creased, where the density is high. If we could read the full phase space of the dark matter, we could rewind the movie. We could see the trajectory of the Milky way back to the Big Bang. The information is there, held in the cold, silent drift of the particles. This brings us to a philosophical confrontation with the Copernican principle. Copernicus taught us that the Earth is not the center of the solar system. Shapley taught us the Sun is not the center of the galaxy. Hubble taught us the galaxy is not the center of the universe. And now, the study of dark matter teaches us that we are not even made of the primary stuff of the universe. We are the foam. We are the minority to an alien observer made of dark matter. If such a thing were possible, the beautiful spiral arms of the stars would be insignificant, a faint tracer of light in the massive, complex, and rich structure of the dark halo. They would study the dark web as the real universe and look at the baryons, the protons and neutrons, as a nuisance, a baryonic bias that complicates their clean gravitational equations. We are the ghosts in their machine, and yet it is the baryons that shine. It is the ordinary matter that can form complex molecules, that can condense into planets, that can give rise to biology, to consciousness, to eyes that can look up and wonder. Dark matter provides the cradle. Ordinary matter creates the life. The drift of the dark matter created the quiet, gravitationally stable environments necessary for billions of years of evolution. Without the dark matter holding the Milky Way together, our sun would have been flung into the void long ago. Without the filaments feeding gas to the galaxies, star formation would have ceased before the Earth was born. We are here because the dark matter drifted, because it slumped, because it held on. We are the beneficiaries of the dark sector's labor. As we continue our surveillance of the sky, new anomalies hint that the story is not quite over. The Hubble tension, a significant disagreement between the rate of cosmic expansion measured from the early universe and the late universe, suggests that our model of the dark sector is incomplete. Perhaps there is an early dark energy that existed briefly after the Big Bang and then vanished. Perhaps dark matter interacts with dark energy in a way we have not modeled. A coupled dark sector, where energy flows between the two fluids, altering the drift over time. These tensions are the cracks in the wall where the light comes in. They tell us that the script of the universe is still being written, or rather, that we are still learning to read the language. In the laboratories of the future, we may finally catch the particle. Imagine the paradigm shift if a detector in South Dakota suddenly lights up with a confirmed signal. We would know the mass of the ghost. We would know its cross-section. We could then simulate the universe with perfect accuracy. We could predict the drift of every halo. We could confirm if the center of the galaxy is full of annihilating particles. It would be the final piece of the Copernican revolution, the moment we physically touch the dominant material of reality. Until then, we are detectives, deducing the shape of the invisible man by the footprints he leaves in the snow. The footprints are vast. The Great Wall, the Sloan Great Wall, the Boss Great Wall. These are structures of dark matter spanning billions of light years, the largest things that have ever existed. They are the continents of the universe, and we are tiny ants crawling on a single grain of sand on a beach at the edge of one of these continents. The drift of these walls is slow, majestic, and indifferent to our presence, but by understanding it, we extend our minds to encompass the scale of the real. We stop being creatures of the earth and become citizens of the web. As we approach the final movements of this narrative, we must prepare to synthesize the journey. We have traveled from the hot, dense soup of the Big Bang, where dark matter was the seed, through the epochs of structure formation, where it was the builder, to the present day, where it is the invisible glue, and into the future, where it will be the lonely survivor. The drift is the timeline of the cosmos. It is the metronome of eternity, beating a slow, gravitational rhythm that underpins the frantic dance of the light. In the final part, we will bring this cosmic symphony to a close. We will look at the ultimate legacy of the dark matter research, the profound shift in human consciousness it represents, and leave with a final image of the universe that is both humbling and elevating. The dark is not empty, it is full. The silence is not an absence of sound. It is a frequency we are just beginning to hear. The drift continues, and we, for a brief, shining moment, are awake to witness it. To truly internalize the reality of the dark matter drift, we must attempt to visualize the universe not as a collection of objects, but as a continuous, flowing topography of density, a landscape where the mountains are invisible and the valleys are deep wells of gravitational potential. The visible universe, the swirling galaxies, the burning stars, the glowing nebulae are merely the snowcaps on the highest peaks of this invisible terrain. If we could switch our perception, trading our electromagnetic eyes for gravitational sensors, the night sky would undergo a terrifying and magnificent transformation. The darkness would vanish, replaced by a blinding luminescence of mass. We would see the great halo of the Milky Way not as a void, but as a towering, brilliant sphere, extending far beyond the disk of the stars, brighter in the center, and fading softly at the edges. We would see the subhalos, thousands of them, moving like fireflies within the greater glow, some containing the tiny sparks of dwarf galaxies, others completely dark, silent wanderers passing through the disk. We would look out into the intergalactic deep and see the filaments not as emptiness, but as blazing rivers of light, connecting the massive, burning nodes of the clusters. In this gravitational vision, the universe is a blindingly bright web of connection, and the voids are the only true patches of dark, deep, spherical caves of emptiness, where the density drops to near zero. In this view, we realize that we have been staring at the negative space for our entire existence, mistaking the shadows for the substance. This shift in perspective brings us to the profound realization of our own intimacy with the dark sector. We often speak of dark matter as something out there, a cosmic glue holding the clusters together, but it is also in here. The drift is local, the phase space of the dark matter, halo, the mathematical description of the position and velocity of every particle, is folded and complex. Theoretical physicists describe the dark matter distribution not as a smooth fog, but as a fine-grained sheet that has been folded over on itself billions of times, like a cosmic origami or the layers of a quasar. This dark matter sheet twists and turns in six-dimensional phase space, and where the folds pile up, where the sheet crashes into itself, we get caustics, regions of infinite density in the mathematical limit, or extremely high density in reality. It is possible, perhaps even likely, that our solar system is currently passing through one of these fine-grained streams or caustics. If so, the density of dark matter in your room right now could be significantly higher than the average galactic background. These particles, ancient remnants of the Big Bang, are streaming through your body at hundreds of kilometers per second. A silent, invisible rain that has been falling for 13 billion years. They are the ghosts of the beginning, passing through the fleeting matter of the present, linking your physical existence to the primordial fireball. There is a haunting beauty in the music of this structure. While sound cannot travel through the vacuum of space today, the early universe was different. It was a dense, hot plasma, a fluid where pressure waves, sound could travel. These sound waves were generated by the fight between gravity, pulling the dark matter and baryons inward, and radiation pressure, pushing the baryons outward. These oscillations, known as baryon acoustic oscillations, BAO, rang through the infant universe like a bell. They were sound waves with a wavelength of hundreds of thousands of light years. When the universe cooled and became transparent, these sound waves were frozen in place, imprinted on the distribution of matter. The cosmic web is, in a very literal sense, a frozen symphony. The distance between the galaxies, the characteristic scale of the voids and filaments, is determined by the pitch of that primordial sound. By measuring the distribution of galaxies today, by looking at the clustering of the Sloan Digital Sky Survey or the BOSS data, astronomers are reading the sheet music of the creation. We are seeing the ripples of a sound that rang out before the first star was born. A deep, resonant hum that organized the drift of the dark matter into the harmonic structure we see today. The drift is the physical manifestation of a cosmic song, the silent rhythm of gravity. This interconnectedness extends to a resemblance that has fascinated scientists and philosophers alike. The striking visual similarity between the cosmic web and the neural network of the biological brain. When we look at a simulation of the dark matter filaments with their branching tendrils and dense nodes, and compare it to a microscopic image of a neuron with its dendrites and axons, or a slice of the mouse cortex, the resemblance is uncanny. A study published by astronomers and neuroscientists in Italy quantitatively compared the two networks, the network of galaxies and the network of neurons. They found that despite the difference in scale, one spanning billions of light years, the other mere micrometers, the statistical properties of the connectivity are startlingly similar. Both systems optimize for the transfer of information, or matter/energy, across vast distances with minimal structure. Both systems are complex networks that sit on the critical edge between order and chaos. While this does not imply that the universe is a giant brain, gravity dictates the web, while electrochemical signaling dictates the brain. It does suggest a universality in the laws of self-organization. The drift of dark matter follows the same structural logic as the growth of thought. The universe builds complexity using a dendritic architecture, a branching tree of invisible matter that supports the visible fruit of the stars. Just as the branching structure of our neurons supports the phenomenon of consciousness, we are the thinking matter of the universe, contemplating the structure of the non-thinking matter that mimics our own mind. However, the drift is also a story of fragility. The existence of life, the existence of observers, is deeply tied to the specific properties of dark matter. If the dark matter were slightly warmer, meaning its particles moved slightly faster in the early universe, the smallest filaments would have been washed out. The fine structure of the web would have been erased. Dwarf galaxies would not have formed. The hierarchy of structure would have been truncated. If the density of dark matter were slightly lower, the expansion of the universe might have won the tug-of-war too early. Structures would not have collapsed. Galaxies would not have formed. The gas would have remained a thin, expanding soup, never igniting into stars. We would not be here. This anthropic principle suggests that we observe the amount of dark matter we do, because it is the amount required to build a habitable universe. We are living in a Goldilocks dark matter halo, not too dense to cause frequent, catastrophic collisions that would sterilize solar systems, and not too sparse to allow the gas to escape. We are the survivors of the drift, the beneficiaries of a cosmic tuning that allowed complexity to emerge from the chaos. As we deploy the next generation of instruments, we are moving from the era of mapping to the era of archaeology. The Gaia mission, a space telescope currently orbiting the Sun, is creating a precise three-dimensional map of over 1 billion stars in our Milky Way. It measures their positions and their velocities with such precision that it can detect the tiny wobbles caused by invisible companions. Gaia is effectively weighing the Milky Way, star by star, by analyzing the motion of these stars. Astronomers are reconstructing the history of our galaxy's formation. They are finding phase space structures, groups of stars that are moving together, sharing a common origin. These are the debris of smaller galaxies that fell into the Milky Way billions of years ago, shredded by our dark matter halo. We are seeing the accretion history of our home. We are learning that the Milky Way is a cannibal, a monster that grew by consuming its neighbors, driven by the insatiable gravity of its dark matter core. Gaia is allowing us to see the scars of the drift, the merger trees that show how the dark matter halo was assembled over eons. We are realizing that the smooth halo is actually a messy, turbulent, lumpy graveyard of ancient galaxies, a swirling, chaotic sea of dark currents that is still settling down. The future of this exploration lies in the convergence of the very large and the very small. We are approaching a neutrino floor in our direct detection experiments. Neutrinos, the ghostly particles produced by the sun and cosmic rays, interact so weakly that they usually pass right through detectors. as our dark matter detectors become more sensitive, they will soon start detecting neutrinos in large numbers. The background noise will become deafening. Distinguishing a dark matter signal from a neutrino signal will be the ultimate challenge. It represents a boundary of human knowledge, a foggy limit where the known ghosts, neutrinos, obscure the unknown ghosts, dark matter. At the same time, gravitational wave observatories like LIGO and LISA are opening a new window. When two black holes collide, they ripple the fabric of space-time. By studying the distribution of these black hole mergers, we can infer the properties of the dark matter halos in which they reside. We might even detect primordial black holes, hypothetical black holes formed in the first second of the universe, which some theories suggest could make up a fraction of the dark matter. If dark matter is composed of black holes, then the drift is not a flow of particles, but a swarm of holes. A terrifying thought of a universe filled with invisible punctures. Yet, despite the terror of the void and the cold indifference of the physics, the narrative of dark matter is ultimately one of unity. It teaches us that nothing is truly isolated. The galaxy that seems alone in the night sky is connected to us by a 10 million light-year filament of dark matter. The atom in your finger was forged in a star that only formed because a clump of dark matter pulled the gas together. The expansion that threatens to separate us is fought inch by inch by the gravity of the dark sector. We are part of a continuous, majestic flow. The drift is the heartbeat of the cosmos, a slow, rhythmic contraction that fights the dying of the light. It is a reminder that the visible world, the world of politics, of biology, of light and color, is a thin veneer over a much deeper, darker, and more fundamental reality. We are the foam on the ocean, fleeting and bright, while the deep, dark currents move beneath us, ancient and powerful, guiding our course through the void. As we stand at the end of this narrative journey, we must accept that the mystery is part of the beauty. We may find the particle tomorrow, or we may never find it. We may realize that our theory of gravity is wrong, or we may confirm that the universe is filled with a new exuberance of particles we never imagined. But the structure, the web, is real. We have seen its shadow. We have felt its pull. We have mapped its valleys and its peaks. We know that we are drifting. We are not static points in a static box. We are travelers on a great, invisible river, flowing from the fiery density of the Big Bang toward the cold, expanding horizon of the future. The dark matter drifts, and the stars drift with it, and we, the observers, drift with the stars, eyes wide open in the dark, watching the shadows for a sign of the substance that holds us all together. In the quiet culmination of our journey through the invisible, we arrive at a vantage point that offers not just a view of the universe, but a reflection on the mind that seeks to understand it. The story of dark matter, this grand, encompassing narrative of the drift, is the story of humanity awakening to the true scale of reality. For thousands of years, we believed that the visible world was the totality of existence, that what we could touch, see, and measure with light was all there was. But the slow drift of the cosmic web has taught us the ultimate lesson in humility. We are the anomaly, the glowing matter, the protons, the neutrons, the electrons that make up our bodies, our planets, and our stars are merely the rare, luminous debris floating on a vast, dark ocean. We are the froth on the wave, not the water itself. To accept the existence of dark matter is to accept that the universe is largely composed of something we cannot hold, something that passes through us without acknowledgement, something that shaped us without our consent. It is to accept that the principal architect of our origins is a ghost. As we look toward the horizon of future discovery, we must consider the possibility that the drift is even more complex than our current models suggest. We have spoken of cold, dark matter, of particles that move slowly and clump together. But the universe often resists our desire for simplicity. Theoretical physicists are now exploring the concept of a dark sector that is as rich and varied as the visible sector. Just as ordinary matter interacts through electromagnetism, the weak force and the strong force, perhaps dark matter has its own forces, its own dark electromagnetism, mediated by dark photons. In this view, there could be dark atoms, dark chemistry, perhaps even dark stars, compact objects that burn with invisible energy, radiating dark light that we can never see. The cosmic web we map with our telescopes might be just one layer of a multi-layered reality, a shadow ecosystem existing in parallel with our own, interacting only through the shared language of gravity. The drift, then, would not just be the movement of a single type of particle, but the flow of an entire shadow universe, a complex, invisible mirror world gliding through our own. This notion transforms the cosmic web from a skeleton into a nervous system. If dark matter interacts with itself, if it has structure and complexity, then the filaments are not just dead highways of mass, but active conduits of a physics we have yet to comprehend. The dark drift becomes a dynamic, evolving process, a metabolism of the cosmos. We are currently blind to this potential complexity, limited by our reliance on light. But the subtle discrepancies we observe, the Corcus problem, the satellite alignments, may be the first hints of this hidden richness. We are like deaf observers watching a symphony. We see the movements of the musicians, the galaxies, but we cannot hear the music, the dark forces we can only infer the rhythm from the swaying of the instruments. The legacy of the dark matter drift is also a legacy of time. The structures we see today, the Great Wall, the Perseus-Pisces chain, the Shapley supercluster, are artifacts of the past because light takes time to travel, and because gravity acts over eons. The web is a time machine. When we look at a distant filament, we are seeing the drift as it was billions of years ago. We are seeing the ghost in its youth. This temporal depth allows us to witness the assembly of the universe, to watch the slow breathing of the dark matter halo as it pulls the gas in, but it also reminds us of the limits of our reach. There is a cosmic horizon, a boundary beyond which we can never see, and more importantly, beyond which we can never influence. The expansion of the universe is carrying the outer edges of the web away from us, faster than the speed of light. The drift is taking the rest of the universe beyond our grasp. We are creating a map of a territory that is slowly deleting itself from our reality. And yet, the knowledge of the drift changes our relationship with the immediate night sky. When you look up at the Milky Way, arching across the summer sky like a river of milk, you now know that you are seeing only the spine of the beast. You know that surrounding that river of light is a vast, spherical halo of darkness, extending hundreds of thousands of light years into the void. You know that this halo is rotating, that it is lumpy, that it is scarred by the impacts of past mergers. You know that the stars are merely the tracers, the bioluminescent plankton caught in the currents of a dark sea. This realization adds a depth to the beauty of the stars. They are not just burning spheres of gas. They are the visible evidence of the invisible hand. Every star is a testament to the success of a dark matter well. Every galaxy is a victory of gravity over expansion. The search for the particle, the physical grain of this dark sand, remains the holy grail. Whether it is found in a vat of liquid xenon deep underground, or detected as a missing energy signature in a particle collider, or heard as a radio whisper in a magnetic cavity, the discovery will mark a turning point in human history. It will be the moment we touch the other. It will be the moment we prove that the ghost is real. But even if we never find the particle, even if dark matter remains a gravitational enigma, defined only by what it does rather than what it is, the concept has already served its purpose. It has forced us to expand our definition of reality. It has broken the solipsism of the visible. It has shown us that the universe is not built for us, or by us, or of the same stuff as us. We are guests in a dark house, living in the few illuminated rooms, while the vast, dark corridors stretch out in all directions, filled with a presence we can feel, but cannot see. In the far future, when the history of human science is written, the discovery of the cosmic web will likely be viewed as our greatest cartographic achievement. We mapped the invisible, We traced the filaments of nothingness across the abyss. We weighed the shadows. This map tells the story of the Great Drift, the process that took a smooth, hot, featureless universe and sculpted it into a complex, majestic hierarchy of galaxies. It is a story of accumulation, of patience, of the slow victory of gravity. It is a story that is still being written as the Milky Way falls toward Andromeda, as the local group slides toward the Virgo cluster, as the filaments stretch and thin under the relentless pull of dark energy. The drift continues. It is happening now, in the silence between the stars. It is happening in the room where you sit, as the dark particles stream through the walls. It is happening in the void, where the lonely dwarf galaxies are slowly falling toward the filaments. The universe is a river of dark matter, flowing from the beginning of time to the end of time, and we are just watching the current. The story of dark matter is the story of the universe's body, its bones, its blood, its breath. It is the story of the dark mother that held us, the dark scaffold that built us, and the dark horizon that awaits us. As we close this narrative, let us hold a final image in our minds. Imagine the universe not as a collection of bright dots, but as a vast, three-dimensional lattice, a web of violet mist stretching across the infinite black. The mist is thickest at the nodes, where the bright jewels of the galaxy clusters reside. It thins out into the long, delicate filaments that bridge the gaps. Between the filaments are the deep, empty bubbles of the voids, and the whole structure is moving. It is breathing. It is drifting. The mist flows slowly along the filaments, pouring into the clusters. The voids expand, pushing the mist apart. It is a slow, silent, majestic dance of shadows, a choreography of gravity that has played out for 13.8 billion years. This is the cosmic web. This is the home of the dark, and somewhere, in a tiny, glowing speck of light within one of those violet knots, a species of curious bipeds has just opened its eyes, looked into the dark, and whispered, "I see you." The drift is slow, the web is vast, the dark is full, and the story of the universe is written in the invisible ink of gravity, waiting for us to read it. One galaxy, one filament, one shadow